Back to where we were in the previous lectures. This is the exam. Okay. I will talk more about the exam later on, but today, very important, we need to continue to learn a different method in optimization. So in today's topic, we're still teaching unconstrained optimization. And in today's method, we're going to learn something called steepest descent method. So in this method, there is one procedure very important that is called line search. Inside steepest descent, there is something called line search or linear search, whatever, they are the same. That procedure is so important, and but it's a little confusing. So today you must pay attention on line search. Otherwise, you may not be able to understand what's going on. Once you get the point about line search, then this is actually a very simple method. Mathematically, it's very simple, but this method actually iterates slowly. So it's not a very good method. However, there's still a lot of people using it. When you see decent method, many people still use this method, okay? Because it's simple, okay? Now let's review what happened when we learn about Newton's method. So for example, in the design space, if there's a 2D design space, I'm viewing the world from above, and for example, I have a function looks like this. This is the contour of the objective function. Also, it's a random contour I made. So let's say this is function f of x. And let's say going this direction, it's so-called a descent direction. Going down is descent direction. Okay? So from this drawing, you can tell your optimal solution probably is right here. This is your optimal solution. But you have no idea the optimal solution is right there. So you may have an initial guess right here. For example, this is your initial guess. So what we did in the past, we used Newton's method to figure out some very important information. One thing is the gradient, okay? So, in fact, the gradient direction is perpendicular to the contour. So this is actually the gradient direction, and it's actually perpendicular to the f contour. Okay? So if we move along the gradient direction, actually we are moving away from the optimal. So this is so-called the gradient direction. If we move along gradient direction, we are moving away from minimum. So what we should do is actually to move along the negative gradient direction. Because when we move along negative direction, the function value drops. We are trying to find minimum, right? That's why we need the negative direction. If we move a little bit along x, function value drops a little bit. Okay, so we want to move along negative gradient direction. So function value f decreases. Okay? And let's recall Newton's method. When we have Newton's method, we have something like this. Right? Newton's method. So over here you can tell Newton's method is trying to move along negative gradient as well, but Newton's method has something more. Newton's method has the information of second order derivative. So this is like the weapon of Newton's method. This is a matrix contains second order derivatives, right? So what does that matrix do? That matrix will change the direction of negative gradient. It changes direction of negative gradient. It's a matrix multiplying with negative gradient, right? So it will change the value a little bit. So what Newton's method does was making a change. So maybe I use a different color right here. Maybe I use a dash line. Okay? So that dash line, that dash arrow represent what happened to Newton's method. It's moving along negative Hessian inverse times gradient direction. It's moving along that direction. And negative Hessian helps correct the moving direction. So it helps correcting the moving direction. So it also has a different function. It tells the algorithm how far it's gonna move. So it tells, or it provides how much or how far we should move. Okay, so Hessian matrix is so powerful. It tells you where to go and also how far you should go. Okay, it's very powerful. But in your exam, you already try it. It takes a lot of time to compute. So nobody likes Hessian inverse. It's a huge matrix, you have a lot of items to compute, and you need to do inverse. Okay, nobody likes it. So can we create a different method? Maybe we can still find a solution without using Hessian. Okay, so in today's method, steepest descent, this is the main purpose of using steepest descent is to avoid using Hessian matrix. So steepest descent. For this method, what's happening is, since this is the first time I write down the general equation, I'm not going to be lazy. I'm going to write down more complete information. So I'm gonna keep the brackets, okay? So here, there is something called alpha times gradient. I'm writing down the most complete information. So this is exactly what steepest descent utilize. And there is something called alpha. And what is alpha? We sometimes call it step size. Why do we call it step size? Negative gradient is still there. Negative gradient is still there, right? Negative gradient tells you the direction. Combining together, negative gradient basically is the direction, steepest descent direction. Steepest descent direction. So we are actually moving toward the steepest descent direction. However, we don't know how far we should move. We only know the direction. We don't know how far we should move. So alpha is how large the step is. That's why we call step size. Okay? So if you are using steepest descent, you need to determine the step size. Otherwise, it doesn't guarantee finding the optimal solution. Okay? So I will give you some time to digest what I just said. Any questions so far? Okay. So let me use the configuration to show you what is going to happen. So let me go back to here and make a copy of the drawing. No. Okay. No. Okay. So what happened in steepest descent is that if you have a starting point, for example here, let's say this is the initial gas, and we are moving toward the direction that is perpendicular to the contour, perpendicular. So it would be somewhere along this direction, right? Because this is perpendicular. Okay, so the moving direction is going to be something like this. This is actually the negative gradient direction. Okay? And we need to find the minimum point that is on top of this direction. So there's a procedure, so-called the line search. And in this figure, you probably can tell maybe this is the minimum point. So we need to find, or we should say, we should find the also it's an optimal step size that brings the design point to the minimum along or on the negative gradient direction. So basically we're trying to find some step size. It's an optimal step size that will make sure you are finding the minimum. Okay? So this is the procedure. Oops. The procedure is called line search. So it's a alpha minimization sub-problem. It's an additional procedure to be solved. It's a sub-problem, and it's an alpha minimization problem. I will tell you what's going on about this alpha minimization. Before I start to talk about it, let me show you what will happen in the next configuration, in the next iteration. So since we are trying to move along the perpendicular direction, so in the next step, we are actually moving along this perpendicular direction. So you actually will you will see the 90-degree between the first moving direction and the second moving direction. Okay? So, on this second iteration, in this second negative gradient direction, you may find the minimum point somewhere here. Okay, and you will be doing this repeatedly, and you will see this kind of zigzagging motion. So the iteration process look like this. This is so-called a zigzag or zigzagging. Okay, usually the procedure of steepest descent, it's always moving like this, always making a 90-degree turn in the design space, and then doing the zigzagging. And this is why it usually takes more iterations to complete, because you are zigzagging. You are not making a right turn and then just move toward the minimum. You're doing this zigzagging, right? imagine you are crossing the street and you are doing zigzagging. You are wasting your time, right? But this is what it is. This method behaves like this. It's simple. When you can understand what's going on in this steepest descent, later on in the next lecture, I'm going to show you a different method called conjugate gradient. Conjugate gradient is a smarter method. It will change its moving direction and also apply line search. So it's a smarter method that can learn from the past and improve the moving direction. So that method that we are going to introduce next time is a better method. But mathematically, the next method is more difficult to understand. Today, in this method, it's easier to understand, but not effective. This method is not effective. Okay, so now let's begin to learn about steepest descent. The best way to learn about steepest descent is to show you how to solve it. So directly show you what to do. So here's one example. Let's just solve a very simple problem. Minimize x1 squared plus 10x2 squared. Very simple problem. The solution is 0, 0, but we need to pretend we don't know. So we have a initial guess, some random number, for example, 5, 5. Okay? And if we do first derivative, if we do evaluate the gradient, it's gonna be 2x1 squared, 20x, no square, 2x1 and 20x2. That's your gradient vector, right? Now, I'm going to proceed the steepest descent procedure. So the next step will be formulating this equation. I'm going to formulate this equation. So what's gonna happen is, at the beginning I have k equals to 0. So x1 equals to x0 minus alpha 0 times gradient 0. So it's going to be 5, 5 minus, we have no idea what alpha is, and we know the gradient, we just need to substitute 5, 5 into the gradient vector, so it's going to be 2 times 5, 20 times 5. Okay? So at the end, we have 5 minus 10 alpha 0, 5 minus 100 alpha 0. So alpha is unknown right here. Alpha is unknown. So what can we do next? Next, we're going to begin the procedure, so-called the alpha minimization. So over here, we are moving on to a sub-problem. Okay, and the sub-problem will be, hold on, let me correct here. I'm going to call this function as f of x. Okay, I forget to do that. So in the sub-problem, I'm going to do this. I am going to minimize f again, but this time I'm going to plug in the current x. So I'm going to plug in x k plus 1. Okay, I'm going to minimize this function. And what is our current x k plus 1? It's actually, let me use green. this is our current xk plus 1, and this is what we have right here. We're plugging in the function, just plug in. So if we plug in, what's gonna happen is, what is our x1? x1 is 5 minus 10 alpha squared plus 10 times, what is our x2? 5 minus 100 alpha squared. I'm just plugging in right here, like this. I use that new equation I have for xk plus 1. I just plug in back to our original function. Just plug in. And from here you can tell it becomes a new function with only alpha left inside the function. There's only, the unknowns are alpha. So it becomes a single variate minimization problem, right? So it's actually becoming something like this, minimizing f of alpha. It's a single variate, one-dimensional problem. So this is the subproblem, so-called the line search, actually. This is the line search. So how can we solve for how can we get the optimal alpha? You can use any method you want. So far, we only know Newton's method, right? So over here, I'm going to use one-dimensional Newton's method to solve for line search. But that is not the only way. There is a very stupid way to do it, is to gradually increase alpha, gradually increasing until you find it. Don't use that method. That's the stupidest method. Increase a little bit, check if it's optimal. No, increase a little bit, increase a little bit. Okay? Don't use that method. We call that kind of search exhaust search. So over here, do not use exhaust search. What is an exhaust search? Just search gradually from the beginning and keep on moving until you find it, the stupidest way. Okay, in Chinese we call it a 地毯式搜索. It's like you are searching, you're searching in the entire space until you find it. We don't do that, okay? So how can we do this exhaust search? It's easy. You can start from some initial guess, for example, n, and then increase alpha a little bit, right? And then check if it's optimal. If not, then keep on increasing until you find it. It's the stupidest way. Don't do this, okay? And in many papers, they do this. Or they define some kind of strategy to determine how far this alpha should be increasing. Don't do this. Please, in your thesis, don't do this. It's such a in ineffective way. So actually right here we can use Newton's method. So now we are going to use one-dimensional Newton's method to find the optimal alpha. Okay? So let me show you how it could be done. So in fact, we are minimizing this f alpha, and the function we have right there at the top, it's 25 minus 100 alpha plus 100 alpha square plus 10 times 25 minus 1000 alpha plus 10,000 alpha square. So I put them together at the end. It's a very, it is what it is. It's a very large function. So it's gonna be 100 alpha square minus 10,100 alpha, blah blah blah, plus something at the end. That thing at the end doesn't matter. I'm being lazy. Or let me just do it. Sorry, the first time I shouldn't be lazy. So it's gonna be 275. Okay? So how do we solve for Newton's method? So in this subproblem, I'm naming the iteration index as m. Okay, so we start with m equals to 0. By the way, if I didn't tell you in the past, this is my with. This is my without. This is my because. Okay? Just to let you know when you see these. Okay? So let me continue. But you need an initial gas, right? So let's start with initial gas alpha. So this time I have alpha m equals to 0 because the index now I use m. It's a subproblem and it's different from k. And I'm using a new index. Now I'm using m, and m starts with 0. So I need an initial gas. I can say 0 just to make my life easier. And also using Newton's method, I need to evaluate f prime, right? So f prime is gonna be 200 alpha minus 100, right? Just doing first order derivative. Now, Newton's method, alpha m plus 1 equals to alpha m minus f. I need f double prime, sorry. I forget about f double prime. The f double prime of alpha is going to be 200, right? So minus f prime of alpha m over f double prime alpha m, right? So what you get at the end, this is 0 minus negative 10, 100 over 200. And I'm going to use calculator to get the right number. over. So that would be 0.05. Okay, and I need to check the convergency. The new value minus the previous value equals to this. So this is not very small, so it's still larger than 10 to the power of 3, negative 3. So I need to continue, okay? So now n equals to n plus 1, and I need to do this again. So this now we have n equals to 1, right? So alpha 2 equals to alpha 1 minus f prime of 1, f double prime of 1. So plugging in, I should have 0.05 minus, now I'm plugging in 200.05 minus 10, 100 over 200. So at the end, calculating 200 times 0.05. Okay, so this is minus 110, 10, 100. So this is like a negative 90, 200. Okay, so this is so small. 90 over 200 is so small. So, at the end, you almost get 0.5 again. Almost. It won't be exactly 0.05 because of rounding, but almost the same. So when you check again, the latest one minus the previous one will be 0.05 minus 0.05. So at the end it's 0. It's already smaller than 10 to the power of negative 3. Okay, converged. Alright? So over here I could say the alpha star equals to alpha 2, which is 0.05. That's the optimal solution for this particular line search. So what you get at the end will be returned back to the earlier procedure, and that's the step size for your original movement along the negative gradient. And this value, 0.05, guarantees you finding the minimum along that line. Okay, so now how do we go back? We were here. Let me copy these. We were here. Now we are going back. Copy those. So paste them here and get rid of something here. Okay, so return alpha star back to original procedure. And this was the original one, right? So over here we basically use the alpha star to replace what we had earlier, the unknown alpha. So over here at the end we end up with 5 minus 10 times 0.05, 5 minus 100 times 0.05. So let me do calculator. So this is 4.5. So this is actually 45, negative 45. Does that make sense? No. No, it was 0, sorry. Yeah. Because of round of error, yes. So in this particular case, we are not moving exactly perpendicular, is it? I think we are. Anyway, we'll see. If we move back to 0, then the 0.05 was not the exact correct alpha. I did some rounding on alpha. So if when I calculate alpha so precisely, at the end, we won't be able to reach 4.5 and 0. It will be some other point. Okay, but in this particular problem, if we reach 4.5 and 0, it actually helps us. I can show you later on by a MATLAB code. Okay. So anyway, this is the procedure for just only the first iteration. So what you need to do next is to check convergency. So you are going to compare the current one and the previous one. So it's gonna be 4.50 minus 5.5. So this is definitely not not very close. So definitely larger than 10 to the power of -5. So not yet converged. And what you do next is to advance your iteration number by 1 and continue the same procedure. And then continue. Until you reach convergence. Okay? So I'm going to write down the general flow chart of steepest descent. So let me show you. First, you need initial gas. And k equals to 0. This is what you have at the beginning. And then for steepest descent, you only need to evaluate the gradient. You don't need to do Hessian. Next, we're going to do you're going to apply what you know to the general equation of steepest descent. Right? So once you have it, you are moving on to a sub-problem. So you are actually solving f of x k plus 1, where you end up with the variable alpha k only. So it's a alpha minimization problem at the end. So over here in the subproblem, we will start with an initial gas, and the iteration index, we use m. Okay? Over here, I was using Newton's method. So over here, I'm using Newton's method to solve for the linear procedure. So for Newton's method, what you need to do was you need to do f prime of m and also f double prime of m. and then you will apply it to the general equation of Newton's method. So f m plus 1 equals to alpha m minus f prime of m over f double prime of m. Right? This is the general equation of 1D Newton. And then you need to do convergence check. So we check whether alpha m plus 1 minus alpha m is smaller than 10 to the power of 3. You check whether this is true or not. Okay? So if not, you will go back to here. If no, then n equals to n plus 1. So if yes, your alpha star is the latest one, the last one. Once you have alpha star, you will then update this value to alpha k. So once you update, your original procedure has a value of alpha. So your steepest descent completes. Then you need to check whether you reach convergence in the original procedure. Over here I made a mistake. The absolute sign on the right hand side only needs one line because it's a single value. It's a scalar. It's not a vector. So on the left hand side, when you do checking, because it could be a multi-dimensional problem. So on the left hand side, you need two lines to evaluate the norm. So it should be a distance measurement, length measurement of some vector. And you are checking whether it's small enough or not. So you're checking like this. Okay? So if not yet converged, you will go back to here. If not converged, and over here your k advanced by 1. If yes, then converged. Your optimal solution would be your latest one. That's your optimal at the end. This is the general procedure of steepest descent. If you write a computer code, this is exactly what you should do. Okay? So over here, can you use something different? Yes, over here. This is 1D Newton. You can use a different method. This is 1D Newton's method. Can use other methods. But right now you know nothing. So this is why on the yellow part I'm using 1D Newton. Is 1D Newton a good method? Yes, I think it's a really good method because it has second order derivative information. And that helps you to speed up the procedure. Okay, now, any questions? Maybe you don't even know how to ask a question, right? That's the question. That's the problem. You don't even know what's going on. This is just the first time. I'm already making this as slowly as possible, but I know it won't be that easy for you guys. Mathematically, everything looks simple. Just plus, minus, multiplying, first derivative, nothing crazy. But the entire procedure looks a little weird. And especially for the sub-problem on the right, when you try to plug in the equation back to f and solve for single variate alpha minimization problem, it's a little weird. If you have not tried it in the past, you have no idea what's going on. Even you know how to do it, sometimes you have no idea what happened. Yeah. Yes. Okay, good question. So when you, on the original procedure, in every k iteration you have an unknown alpha, only one unknown alpha for each k iteration. In order to find this optimal alpha k, you are moving on to the right hand side. Over here, it iterates as well. So initially you have a guess, and the iteration number starts with n. It's going to iterate multiple times. So over here your alpha will change until converge. But this procedure, no matter how many times it iterates, you ends up with one value, the final one, final alpha. And you will push that value back to here. So for the k iteration, you spend some time right here and get one value back. So the kth iteration completes. Then you move on to here to check whether it's converged. If not, you go back again. This alpha k becomes the next alpha k. So a new alpha k. So this procedure goes again in the next round. Okay? Why is that happening? Because from the configure, like here, when this is the initial direction, initial point. When we decide to move along this direction, over here is like alpha equals to 0. And over here is like you found the optimal alpha star. So anywhere on the line is some step size that doesn't give you optimal. So you are solving Newton's method along this line until you find it. So over here, from this point to this minimum point is a specific distance. Some alpha represent this distance. In the next iteration, you are moving along this direction now. This is a different step size. That's why it should be a different alpha. Okay? Very good question. Any other? Yes?
For the x and the alpha, do we usually use like the same convergence criteria or not?
Say again, sorry.
So for the x and for the alpha, do we usually use the same convergence criteria or not?
Oh, convergence criteria. Okay, that's also a good question. For the convergence criteria, you can define your own way. You can say, I want to be so precise on alpha, or I can be so precise on x, or I want to use a different way to check convergency. Remember earlier we mentioned we can check convergency by comparing f, using the difference of the current f and the previous f. So in optimization, when you write a paper, when you run the code, the way of checking the convergency depends on the user, or depends on the designer, I should say that. So the designer defines how accurate you want the convergence to be. You want to be so precise, you will reduce this value to an even lower one. And usually when you have optimization software, they have the threshold by default. They define some appropriate number for you. But if you want your optimization to be more precise, you can reduce the value here. If you reduce the value here, it will take more iteration to converge. So it really depends on how much computational power you have. Okay? So this equation over here can be changed. Let me give you one example. So this is very good question. This one can be changed to something else. Can be changed to, for example, f k plus 1 minus fk, and whether it's smaller than some value or not. I can change, for example, 4. You can check this instead of this. You can even check both. The convergence check could be heuristic. Do you know heuristic? It's like you can set up multiple guidelines. I even saw, for example, sometimes you don't want the iteration to be too long. So if this iteration reaches the maximum iteration number, you will break the iteration no matter what. But sometimes, for example, the maximum iteration number you wish is 10. Sometimes when you stop at 10, actually the solution was so bad. When you do programming, you decided not to move on to the 11. So you are the designer, you decide how you terminate the process. And that's why whenever you are using optimization, you need to be very careful about the iteration process. Always check whether it's truly convergent. Okay? Similarly, when you use other numerical methods or softwares, for example, is anyone from thermal field or solid mechanics? I think many of you are from thermal or solid mechanics. Sometimes you use finite element softwares, and usually they are solving for also convergence, and usually they will set up termination criteria as well. And if you don't check your numerical software carefully, sometimes the computer stops when the program decides to stop, not because it's precise already. So always check every detail inside the numerical procedure. Okay? Any other questions? Oh yeah, go ahead.
So our goal is actually to find the actual like x, right? So do we really need to calculate alpha to like very accurately or not? So if the convergence criteria for the x is 10 to the power minus 3, do we really need to calculate the alpha to the same accuracy or not? Because the lower the convergence criteria, right, the more iterations it costs.
Good. There's no exact answer, because if you have a faster evaluation of alpha, you may have less accurate alpha, which means you may have stopped the iteration somewhere here, right? And starting from that point, you still can be moving toward some good direction. You never know, because you don't know the shape of the objective function. So sometimes solving for optimal solution is case by case, or it's by luck. and there's no exact way to guarantee how effective the procedure is. So what we usually do in academia is we will define our own settings of everything. For example, what's the maximum iteration number and how accurate each iteration should be, and how we evaluate convergence. We will mention the details so precisely on papers. So when people try to compare their methods with yours, they can use the same settings. So the results are comparable. Yeah. And like I said, there's no exact solution for your answer. For no exact answer for your question. Okay? Any others? If there's no more, I'm going to program right now. MATLAB programming again. Okay? So no more lecturing, just MATLAB programming. Okay. Good. So let's get back to here and turn off this, turn on this guy. Too large. And I need to turn off this guy. Okay. And turn on MATLAB. I need internet. Okay. I need to restart MATLAB. Okay. And let me see, where do I forget where I keep all the files. Oh, here? Yeah, maybe. Okay, so it's fine. Let's create a new file here. So I'm going to name this file as oh, will this be too small? Is it small? Is it small for you guys? Too small, right? Let me enlarge my screen. So I should do. Okay. Where? No. No. Oh, here. Okay. So I should. No, this is not the one. Here. Let me try this. Okay, good. And I should adjust the video recording as well. Not this one. Not this one. Oh, it actually was. Which one? Okay, this one's good. Is it? Oh, this one. Okay, good. Yeah. Then I need to bring myself up. So here. Okay. And maybe I can move down a little bit. Yep. Okay. Should be good. Okay, now get back to MATLAB. Okay. I always do clear CLC and close all. Then what am I going to use this time? Let me teach you how to do finite difference this time. So if I want to do finite difference, I will do finite difference. I just need to substitute. So maybe symbolic again. Symbolic x1, x2, f equals to x1 square plus 10 times x2 square. Let me save this file as Steepest main function. Okay. So now I have a function. What do? I need an initial guess. So let me call my capital X. Let me just name iteration as iter. So iter basically is no. Let me use k. K is 0. No, k has to be 1. Because in MATLAB the index cannot be 0. And I'm gonna use capital X. So this will be my initial get. Oh no. Yes. K. Let me use vertical vector. So if it's a vertical one, it's gonna be this k, or let me use a horizontal one. So k comma and how do you call this? What is Mao Hao? I forget. What is Mao Hao? What is Mao Hao? Column, okay. K, comma, column. Column means everything. Okay? So this is my initial guess. This is symbolic. This is iteration number. Okay, now I need some value called error. Let me just give a large number. While error is larger than 10 to the power of -3, you need to iterate. When the error is large, you need to iterate. Yeah. So this means iteration stops when error is smaller than or equals to 10 to the power of -3. And what you are going to do here is to I'm going to define something called delta. Delta is some value small, and I will tell you what is delta. This is for finite difference. Basically, approximation of derivative. Okay. I will use delta later on. So over here, I will need to compute the gradient. I need a gradient. So grad equals to here's the time to do finite difference. Let me create a for loop. Do I use a for loop? Maybe not. Let me just grad equals to substitute f, and then you need to do what? Substitute. Let me see if I can do this. Let me try something first before I do something. Subs f. Let me try this. x1, x2, 1 and 2. Yes, you can do this. Good. So substituting x1 and some numbers into x1 and x2. So I'm substituting values into both symbols simultaneously. So this time I am substituting my current variable, right? But I'm going to increase the value a little bit. So increase what? Increase delta and 0. Okay. I'm not talking to your Siri. My Siri just say I don't know why. Okay, I'm substituting this, and then I'm not gonna. Oh, I will need some value right here. So f current. So for f current, I'm not doing the delta. I'm just substituting into the function at the current position. So let me call this f dx and f dy. Maybe that's easier for everyone to understand. Okay, so for the dx, basically you advance x by delta. So you plus delta and do nothing on y. And over here you do 0 and then delta here. Okay? So what will be the gradient? Gradient is going to be f dx minus f current over delta. And then the other one, I make it horizontal, that's fine. So the other one is going to be dy. So what's going on? I can show you over here using this. I'm gonna turn on my iPad. Where's my iPad? No, this guy. This is my iPad. Okay. Let me just show you what's finite difference. Just remind you. Whenever I want to evaluate df over dx, I can use f x plus delta x minus f of x over delta x, right? This is simple calculus, but it's only approximation. I just need to make delta x small enough, but it doesn't need to be so small, because the equal sign is only accurate when delta x is infinitely small, close to 0. But in computer, you don't need delta to be so small. Okay? How about gradient? Gradient basically is like this. Partial derivative, right? So what you can do is, you have f. Over here, you basically have your original x and y, but you have delta x summing to summing x summing delta x minus the original one. And over here you have delta x over delta x. And on the other hand, for partial derivative of y, you basically have this delta y here over the original one and delta y. So I'm keeping deltas the same. Delta x and delta y are the same in my code. What I did was I call this f current, and I call this guy f dx, and I call this guy f dy. Basically, this is what happened in my code. Okay? Let's get back to the code. So turn this off, turn this on, get back to MATLAB, and you can see this again. I'm substituting my current x into f, and the next line I'm substituting current x plus a vector, a horizontal vector, where my x is having an increment of delta. And in the next line I'm doing the same thing, but I'm putting an increment of y with delta. Okay? So this is increment of dx, increment of dy. So I name them in this way, and this is how I can change the line so you can read more easily. See, for the gradient, the current one is using the f dx minus f current. The other one is f dy minus f current. Okay? Then you have your current gradient. This is your current gradient. And what we are going to do is to have, basically, I need a symbol called alpha. So let me use symbolic again, and let me create something called alpha. So over here, I will have a new x. So, but this one, I'm gonna call it x alpha. So my new x is gonna be my current x. This is my current x, right? Minus the symbolic alpha times gradient. Okay? Let's run this code for now, just to see what's happening. Okay, let's run this code. So first, over here you can see I have a symbolic function f in the memory already. I move one step forward. I have a capital X matrix with 5 and 5, and then error, delta, and coming into the iteration, I evaluate f current. So what is f current? F current, okay. It's a value, but I need to be careful because right now it's symbolic. That's fine. It's symbolic for now. It's a value 275, but it's symbolic. Then f dx. So when x increase a little bit, my function value becomes some value close to 275, but it's a symbolic equation. It's a 2751001 over 1 over 10,000. So it's some value a little bit larger than 275. The reason why we need this is because we need to evaluate a gradient. We keep on doing this until at the end we will have a gradient vector. So let's take a look at the gradient vector. So over here they are symbolic. The first one is 1001 over 100. The second one is the same. Okay. That if it's the same, it's weird. Let's see. Did I make any mistake? Because the gradient shouldn't be the same. Where? Did I make a mistake? That's C. And then let's check if I plug in what will happen. So x alpha is here. The first one, the second one. They look exactly as, oh no, they are not the same. Yeah, they are not the same. Sorry, I was wrong. This is over 10, this is over 100. They are not the same. The gradient are not the same. Okay? So what my x alpha look like right now? Looks like this. This is what I showed you earlier. We have an unknown alpha here. So now we need to find, we need a subproblem. So here's where we initiate the subproblem. Okay? So what do we do? How do we do subproblem? We need to plug in back to our f. So we need a function called f alpha. So when we plug in, it's gonna be like substituting f, but what we are doing here is actually we are plugging in x alpha into our function. So you will get a function f alpha. So let's take a look what's gonna happen. Run the code until the stopping point here. So now I'm plugging in. What you will get at the end, f alpha looks like a function with a bunch of alphas. Okay. Only this is exactly what I did by hand. Okay. Now we need to find the optimal alpha. So I'm over here. I need to do another run, a smaller loop of Newton's method. So over here I will have initial guess iteration number m. So this is iteration number of subproblem. And I need an initial guess. So over here I'm using capital A as my variables. A m equals to 0. So this is my initial guess of alpha. And I need a different value error, so I'm going to call it error, but for the alpha problem. Also a large value. And while error alpha is larger than 10 to the power of negative 3, I need to do the following. So here I need to do derivative. So here I'm going to plug in f alpha and current. Basically the same thing, substituting into f alpha, and my variable is called alpha, right? And I'm plugging in the current value. This is my current value. Okay, and for finite difference, I need f d. Let me call it d. No, not dx. F alpha. Let me call plus, and there's alpha, and let me call minus. I will tell you what is plus and minus later on. Just let me complete this. So here I'm substituting same thing, but here I'm having a plus delta here and a minus delta here. Okay, and I'm gonna tell you what will be my f double prime f first derivative. So f alpha and d. Let me call the dx. Should I call dx? Just diff, no, derivative, or just a first order derivative. How about this? Just first, yeah, first derivative. So what the result would be using the f plus minus f current over delta. That's first derivative. I need second derivative, so I'm calling this second. The way to do second derivative is gonna be also plus minus 2 times current plus minus over delta square. Okay, what's happening? Let me turn on the iPad again to remind you how to do f double prime. Okay, so if you want to do f double prime, in fact, it's gonna be x plus delta x plus delta x minus 2 times f of x plus x minus delta x over delta x squared. This is finite difference for second order derivative. I'm not going to prove it. You can easily find it from Google or from any lecture you took in the past. I'm not proving it. It's very simple. You can prove it. But just for you to know, this is using central scheme. Central scheme of finite difference. Finite difference. But this one is actually using forward scheme. So I used different schemes. Okay? It's like you are approximating the derivative at the center, or a little bit in the front, or a little bit in the back. Is it okay to use different schemes for finite difference? Mathematically, it's not good because you are estimating the derivatives at different locations. However, for computers, it's fine. The values will be very close. Okay? So get back to the MATLAB code. Now, right here. So this is, see, the one with plus delta minus 2 times the current one plus the one with negative delta, minus delta, okay, over delta squared. So this is how you get second order derivative. Then you will assemble them together. So a m plus 1 equals to am minus first derivative over second derivative. This is basically 1d Newton. Okay, let's see what's gonna happen. Let me stop right here. So run the code. Over here, if I check my a's, yeah, it gives me a different value at the end. Okay, so now I need to do convergence check. So error alpha equals to absolute value of am plus 1 minus am. Okay, and m equals to m plus 1. Advanced by 1. That's it. So this will stop until your error becomes small enough. So at the end, when you are done with this smaller loop, you need to update your alpha outside. So you have your x alpha here. X alpha looks like what? Looks like symbolic. So what you will get at the end is x k plus 1 comma colon equals to substituting to this guy. This was my equation. And over here the so alpha will be replaced by the optimal. So the optimal would be the last one. But in the last line, you already advanced by 1, so you minus 1 here. Okay? The last one. Or you just say end, the last one. So you won't make any mistake. So once you have this, let's see if that truly works. Let's run the code up to here. So you do have a's. See, your a vector starts with 0. The next iteration, you come up with some value 0.0454. The next iteration, 0.0454. So converged. Over here, I'm substituting back to my x. My original x was 5 and 5. When I plug in, now I have 4.5456 and then 0.4555. In my notes, it was 4.5 and 0 because I did rounding of alpha. So my calculation was not accurate enough. But in MATLAB, it's really accurate. The first iteration it was 5.5, and the next iteration it becomes a different point. Okay, so now I need to do convergence check. What I need to do is update the vector value of error. So basically, calculating the norm of k plus 1 minus xk. Okay, that's my error. And then you advance the k by 1. So at the end, you should get your solution. So let's see what's the result. It's taking too long. What happened? If it's taking this long, something is wrong. What's my k at the end? 57 is not finished. So something was wrong. Let me see what happened. Error is the norm. Oh, sorry. Comma, column. Okay, run the code again. Not converged. So 19 iterations. If I ask you to do this in exam, it will take you entire morning to complete 19 iterations. Okay, but hey, show me in a graph, otherwise I can never understand what happened. Let me show you in a graph. Now, before I do that, let me comment on my lines. Okay, let me see. This is evaluating at current point. Evaluate at current point plus current plus delta x, and this is like evaluating at current plus delta y, and this is estimating the gradient using forward scheme of finite difference. Okay, and this is the iterate. How do you call it? There's a name of it. Let me find the right name. Conclude. What's the adjective to describe what you do repeatedly, iteratively? There's a word, I forget. Anyone who's good in English? Okay, there's an adjective describing some mathematical equation. You advance the index by 1 every time. You iteratively, what's the adjective? Increment? No. Concurrently? No. There's a word, because that's the word you should use in papers. I now forget about that. Let me see. No. Not that one. I want to tell you that right word, but my brain doesn't tell me today. What's the word? Anyone? Say again. Yes. Recursive? Recursive. No, it should be recursive. Recursive, I think. Recursive. Is it recursive? Relating, yes, recursive. Because sometimes we call recursive equation, right? Recursive. Is it? Recursive. Recurrent? Recurrent. You keep on doing it again, again and again, right? Oh, recurrence. Recurrent. 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 Like this? R. Right here. RECURRENT, right? Recurrent, right? But I remember in papers we use recursive. This is the same word. It's slightly different. I remember it's called recursive. Let me see. Recursive. Yeah, it's called a recursive formula. For example, let me show you. Recursive formula. If you Google it, you will see a bunch of equations with index telling you how you advance. So usually you call recursive formula. Recursive. Yeah, that's a word I want to use. Okay, so recursive formula for steepest descent. Steepest descent. Steepest descent method, but step size still unknown. Okay, so what you need to do is to substituting back to f to get f of alpha, and then you will be solving for this, and this is where you evaluate f of alpha at current alpha, and this is f of alpha plus delta, and this is basically f of alpha minus delta, and this is basically estimating f prime of alpha, and this basically is f double prime of alpha. Okay, and this is using 1D Newton to find next alpha. Okay, should be very clear. I wrote comments on almost every line. Okay, and this is like updating optimal alpha back to the recursive equation. Okay, good. Now for graphics. For graphics, I need to, let me do this here. Let me define a plotting zone. So negative 10 to 10, negative 10 to 10. And then I will say figure 1. I think one figure is enough. Let me say easy contour F zone. Let's see how it looks like. Okay, it looks like this, and I want to make some corrections. Let me see if I can get GCA line width 0.5. No, I cannot do that. Line width. No, I still cannot do that. Or did I use find? No. I forget what was the command to find that. Get graphic object property. I need an H here. Oh. Or maybe I say HH then equals to this. HH get HH line width 0.5. No. Oh, Too many input? No. Property. How about find? Find. No. How about this? No. Okay. Decide to Google. Find graphic object of easy contour. Really want to get this done. Get. Okay, get. Oh, find object. Ah, yeah. Find object. Yes, I found it. It has been a while. I forget about this command. Find object. Okay, good. Find object. So let me call this H. So I can set H line with 1. Okay, good. 1 is not clear enough. 2. Yes. See, it's thicker now. Perfect. And then x is equal let's see, set GCF color white, set GCA font size 20. Okay. Title off, and set GCF position, let's say 100, 1,000, no, maybe 900. Where is it? Okay, maybe a little smaller, 800. Do it again. Where? Here. Great. This is how you can directly use it for paper. Right? You just copy it and then you can directly use it for papers. And I want this to be dash line style, dash line. Oh, cannot be like this. No, not line style. What's the keyword for it? Yeah, I remember line style. No. Okay. I need to find the proper the name of the field. What was it? The property name. It's called line style. Line style. I had the border as well. So let me do this. Let me stop here. So I have multiple objects. One is the axis, the other one is the contour. So h dot contour. Can I do this? Contour. No, I can only use the second one. Yeah. So the second one, line style dash line. Not the other kind. How about this? Yes. Okay. So if you can write commands to adjust your figures, you don't need to do it by hand. Okay, good. Now I have the proper figure. So next I would like to show the position of my initial gas. So I need to hold on and say plot my current x. I will plot it like a circle and make it red, and the marker size would be 10. Line width would be 2. How come there's 2 of them already? How come there are 2 of them? Who are you? Sorry, I shouldn't do this. I need to assign them one by one instead of assign them at the same time. Okay. Yep. So do it again. This is what I have. This is my initial gas. Now, whenever I find a new position, then I will plot out that new point. So right here, same command line, and I already advanced my k, so this is fine. And I would like to draw a line. So drawing a line would be the kth one, and how about to avoid confusion, let me do k plus 1 afterward. I will draw a line just to show how the iteration look like. So let me make it a straight line, and same color, line width 2 is okay. Okay, do it. How come it's not perpendicular at the beginning? It's supposed to be perpendicular, isn't it? It's always changing its direction. Why is that? I thought it's going to be perpendicular all the time. Final difference. Thank you. You're right. Because so if I change delta to a smaller value, let's see it. Yes, you're right. Thank you. Good job. Yes, because we use final difference, so the gradient was not accurate, and that's why along the linear direction, we didn't find the true alpha star. Good job. Good observation. Thank you. So, what else can we? Earlier we had 0.01 for delta. So, which means when I estimate my gradient, I'm increasing my delta by 0.01. It's not a super small value. So my estimation of the gradient will be a little inaccurate. So if I run the code again, maybe this time I show you this. Draw now. If we do draw now, you will see animation. And maybe we pause a little bit by 0.1 second. Okay, then we can see interesting animation. Okay, but if we change the delta to a smaller value and plot again, you can see it's moving more like a perpendicular direction. Okay, and actually 6 iterations you complete. Besides showing the figure, let's plot out some values so we can read it. Let's display some results. So in order to display the results, right here I'm gonna say at the beginning right here I will say display initial guess equals to a bracket and then my value here, but I need to say number to string, convert into string, and then complete the first expression just to make sure. No, I made something wrong here. Yep, like this. So I will have initial guess 55 right here. Okay, good. Next, I am going to say display the position right here. Whenever I have a new point, I will plot. I will say I will display iteration, and the iteration number would be k, and then comma x equals to a bracket to this, and then this should be k plus 1. And also I would like to know what's the current error. Current error equals to number to string error. Okay, good. Okay, run it. So over here you can see it's iterating. Every time x value change a little bit, your error decreases. So now we stop right here just because we stop whenever the error is smaller than or equals to 10 to the power of negative 3. What if we reduce the tolerance to a lower level? Let's say 10 to the power of 6. Like what you asked earlier. You asked earlier. Let's do that. And you can see it will iterate even more until it really can reach to the 10 to the power of negative 6. It's trying really hard. Trying really hard. It's not converging actually. It's not converging. It won't. So there's a limit. If you set up your convergence criteria, but you cannot reach to that accuracy. Why? Because your delta is only 10 to the power of 3. You may want to reduce the delta to a smaller value. Well, let's see if it really can reach 10 to the power of negative. Yes, it did. So 14 iteration. From here, you can already tell how small your delta is affects how accurate your gradient is, how tight your tolerance is, affects how accurate your iteration could be. And all these parameters affect each other. Okay? If we zoom in to just take a look at what's inside in this region, you can tell it's always moving, zigzagging, like making those 90-degree turns. Over here it's not 90-degree because we may not have accurate enough gradient at this small area. So it's not making 90-degree turns, and it's wondering where to go. Over here, let's zoom in more. What's happening here? I think that's the closest. It's already in the region of 10 to the power of negative 7. So small area, such a tiny small area. Okay? So that's it. How about we try a different position? Try a different starting point. For example, 9, 5. Let's see what's happening. And the procedure won't be the same. And the required iteration to converge won't be the same as well. Will it converge? It should be. No, it's not. Actually, it's not. It's wandering around and it never reaches to the right position. So sometimes you're just not lucky. The solution is there and you are just jumping left and right. Can we improve it? Actually, there's one thing that we didn't do good enough, that is the alpha search. For the alpha search, we stop at 10 to the power of 3. It's much larger than the tolerance we chose for X. So for alpha, maybe we need to have a tight tolerance as well. And let's see if that improves everything. See, it reaches. So now we have better estimation of alpha because we have tighter tolerance for alpha. And let's observe the details when it's reaching closer. Because we are having more accurate alpha, we are almost making 90-degree turns, but not always. The accurate answer should be 0, 0, right? But what we get at the end is 1.2 times 10 to the power of negative 6 and negative 1.5 times 10 to the power of negative 8. It's almost 0, 0, but it's numerically we can never reach 0, 0. Okay? So this is the issue for numerical approach. We can never be accurate. So we can only set up some tolerance. So that's it for today. Any questions? I will give you the code. Can anyone program a MATLAB code like this in a short time? I still make mistakes. I still forget some commands, but just because I have memories of some of the commands somewhere deep inside my brain. Sometimes, like last time, I wanted to use find object, but I didn't Google for it. So last time I gave up. But this time I really want to use it. So I probably spend 1 or 2 minutes to find it. Because I know, when I was a student, I know there's a command, help me do this. But I just forget his name. So you guys need to practice more and keep those somewhere in your brain so that 10 years or 20 years later, you may be using it again. So I knew how to program like this probably 15 years ago when I was a PhD student. I learned nothing more. After PhD, I learned nothing more. Right now, I'm teaching Python and I'm asking my students to use C++ or C#, but I actually cannot program in the same level in Python, C++, or C#, because when I was a student, I didn't use those. I used MATLAB. So a good a good suggestion for you guys as students, you should practice as much as you can. And after graduation, you either move on to a next level, or you find a job, maybe in the industry or in the academia. You are busy all the time. You are busy on what you need to do at the time. And there's no more time for you to upgrade yourself. So, as a student, this is the best timing for you to learn something. You have nothing to do. You only need to take courses, do homework, take exams, learn, review paper, do experiments, write papers, research basically. What does research mean? Research means keep on searching. Research, right? You are researching. You're always searching for something. You're learning something as a student. When you graduate, your learning curve drops. There's no very small, very limited time for you to learn something new after you graduate. So the way I was able to program like this came from my PhD years. It was before 2010. I graduated in 2010. So it's 13 years ago. I was able to do this probably in 2008. So it's really 15 years ago. And if you see a figure like this, in almost all my papers, I have figures like this, because I program MATLAB codes the same way since my PhD years. I never need to improve more. I can already publish papers. So I stopped right there. I didn't spend more time on more programming skills, because that was enough for me. But for you guys nowadays, you need to spend time on what you need to, what's good for you, what's enough for you. You need to keep on learning, keep on practicing until you feel enough. Until you graduate. When is enough? Graduation is enough. If you learn enough, you can graduate. If you didn't practice enough or learn enough, graduation is always far away. Okay, so when I was a PhD student, when I was a master student, I delayed my graduation. It took me 2.5 years to graduate. So I was really sad about postponing my graduation. It took me several months later, extra month for me, So I was not happy. I was sad. Um, I'm not even happy about my advisor at the time. But that was mainly because I was young at the time. I couldn't understand why I cannot graduate in time. Once I move on to a PhD degree, actually I shortened my graduation. I shortened the degree time. For my PhD, only took me 3 years. So in total, 5.5 years to complete master and PhD. So once I started to understand why sometimes I need more time, sometimes I don't, my advisor told me one thing. He said he was not the person to decide when is my graduation. He said, I'm actually the person to decide. And he told me, you will feel ready when you are ready to graduate. So I think many of you are PhD students. You probably cannot see the ending of your degree. It's probably far away. You may be frustrated every day. Don't be. You need to encourage yourself and keep on learning until you accumulate enough knowledge, skills, and learn so much. You will be better than your advisor at some point. Because your advisor is the same researcher 20 years ago or 30 years ago. He didn't improve himself anymore. He just know more about the research itself, but he didn't spend more time to learn the skills. You will be better in those small skills. And you will be better than your advisor at some point, and you will realize, okay, you already learned enough, you are able to deliver enough research results. It's time for you to graduate, because it's time for you to move on, rely on yourself. You don't need to rely on your advisor anymore. That's where you can graduate. Okay? I hope this is helping you guys. Is anyone tired of graduate program? When I was a master student, I feel tired every day. It's so disgusting. I feel like when I was a master, I was in hell. I feel like every day is like in hell. It's so tiring mentally, physically, and nothing was right. But when I was a PhD student, my advisor gave me so much freedom to learn by myself and let me know how to do research, and let me realize what is PhD by myself. So one day I realized, okay, this is how research should be done. And then after you have a change in your mindset, you won't feel upset. You become a really positive person every day. And every morning when you wake up, you feel like you will go out and do something good for the day and feel happy after the end of the day and go back home, have a nice sleep for the day. I feel like for my entire PhD, I was able to work really happily, and I can decide when exactly I want to work, and then take a rest, do whatever I want after work, and then repeat this routine again for the next day. Yeah, so find that kind of lifestyle in your graduate program, because after you graduate, you have no time to find that after you graduate. the lifestyle you have right now will be the lifestyle you have afterward. I am exactly who I am when I was a PhD student. Yeah. And you will be exactly who you are. If you are lazy on something, you will be lazy on something in the future. If you are good in something, you are always good in that. And if you are someone who can learn something new, in the future you still can improve yourself and learn. Okay, so the future will be like magnifying yourself. It's like a magnification of yourself when you are a graduate student. Basically, yeah. I hope those make sense. Okay, any questions for Steepest? Next time I will show you conjugate gradient. Mathematically, it's so complicated. You will be so confused about my mathematical derivation along the process. Every procedure doesn't make sense at that point. You have no idea why we are doing this here, why we are doing this there. But the derivation is so long, the purpose at the end is to collect every mathematical derivation earlier to end up with a very clean equation at the end. That final equation will change this vector. In the first step, conjugate gradient is the same as steepest descent. Move along the same direction, also doing line search, but conjugate gradient will do something to change the second vector. Based on the knowledge of the previous one, conjugate gradient knows I should not move along this one. I should change the direction a little bit, just a little bit. With that change and doing line search toward a better direction, you just can find a better position maybe to here. So next time when we do conjugate gradient with the same setting, we probably can converge in 5 iterations. This one probably 10, but conjugate gradient can converge much, much faster. And conjugate gradient also doesn't need to use Hessian matrix. So the conjugate gradient method is a more advanced method than steepest descent. Okay, so today when you go back, you need to read more about my notes, watch the video. If you have no idea what happened, you must review it. Even you understand, you also need to review it because this is not something you learned in the past. Nobody teach you what is a line search in the past. Nobody teach you what is a sub-problem in optimization. This is probably the first time you learn something like this. So you need to practice, you need to get used to it. Next time when we use conjugate gradient, in the second iteration, we are also using line search. So if you are not familiar with line search, if you have no idea what I'm doing here, then you're in trouble. Because later on you need to, in the exam, you need to solve by hand, right? It's going to be a lot of mathematics in the exam for the next one. Okay, now we should talk about the scheduling. I think we skipped one lecture, so we should be making changes. So, next week is a holiday. Oh, so many holidays. So did we decided to do midterm after the holiday? We already let's see. So when I was in USA, I was supposed to give you a video, and when I come back, I should give you a lecture. But I'm still on the sky. I'm still flying, so I skipped 2 courses. I actually skipped 2. Okay, it's my fault. But I feel like I cannot make videos of lecturing because you can never ask questions. So the video will be so long, so boring, and you just don't know what happened. If I don't spend time on this and answer all the questions right away, it's so difficult for you to understand. So do you want, let me see, the final course would be June 5th. June 5th. Is that the final week? Actually, we can do the 17th week and 18th week, but I will be flying again. So, what do we do? Maybe I will skip some advanced topics in the second half, so you may learn less. Is that okay for you guys? Yeah, because I think though the methods I introduced should be very important for optimization. So I won't skip the materials, but I can teach you less. Like I think in the 10th lecture I mentioned something about I will be talking about multi-objective and multidisciplinary. That probably will be skipped. Okay. And also uncertainty, I guess I will skip. So maybe I will skip those. So we already talked about steepest descent. Let me write down the schedule, otherwise you may not understand what I'm doing. Let me just tell you the schedule. So April 10th, 17, 24, and then May 1st, 8, 15, 22, 29, June 5th. That's it. So this is a holiday. Oh no, 10th is not holiday. Over here we will learn conjugate gradient. So I guess we need to skip. We need to do exam some other time. Do you mind doing take-home exams? Shame on you. Shame on whoever smiled. Okay, we will do take-home exam. So that will cover steepest descent and conjugate gradient. If you okay, because I will be giving you my codes. So if you use my code, it's gonna be so easy, right? But you know, when I give you the problems, I will put some random numbers in the problems. So everyone should be having a different problem. So when you take home, if you have discussion with your friend, I don't even know. I will ask you not to do it, but nobody can tell. Even you discuss with your friend,
you are solving different problems. And even if you are using my code to check the iteration process, you still need to spend time to understand my code. And when you write down, when you do handwriting of the solution process, you need to write it down. So I can still tell whether you are doing it by yourself or not. So I think it's okay to do take-home exams, and it's more relaxed, and it's not that scary. But for the take-home exams, I will give you on specific day, and you need to complete within certain time. For example, I give you only 1 day, something like that. So be aware of the time limit. You probably need to occupy several hours for this take-home exam. So maybe the best timing would be weekends, because you may need to take courses. So for example, one day in the following weekend after April 10th, at some moment I will release the exam sheet, and then the time starts ticking. Before certain time, you need to handwriting. Okay. So that give us 1 more week for lecturing. So after that, I need to talk about linear programming. Very important method. And then something called KKT condition. KKT condition, maybe try to plus quadratic programming. After that, we will have another take-home exam, number 2. For take-home exam, definitely this is LP. LP is the most important one for take-home exams. I'm not so sure about QP, because QP is not that easy. Not that easy for handwriting, because the procedure is so long. Usually, when you are doing quadratic programming, it's relying on computers. If by hand, it's so troublesome. When I was taking an exam about QP, when I was a student, the advisor didn't even give a problem. In the exam, what we need to do was to memorize the derivation of QP. Basically, prove quadratic programming in the exam. That's what we did. Proving is shorter than truly solving. The procedure of solving QP is so long, a lot of math. But proving it is basically symbolic. Everything is simple. But even for proving, it's so long. Okay, anyway, so probably for take-home exam 2, probably focusing on LP. Maybe a little bit of KKT. We can do KKT. KKT is okay. But QP takes a lot of time. Then we need to do proposal. Did we mention about projects? Did I ask you guys to form in groups? Not yet, right? Okay, we have too many students here, so it's impossible for you to present one project per person. I need you guys to form groups to encourage foreigners and Taiwanese work together. I will force you guys to work with Taiwanese mixing foreigners. that's actually good because many of my students are here. My students should be pretty good. Should be. Should be pretty good. So it should be nice to work with my students. Should be. Okay. So I will encourage you to form groups between Taiwanese and foreigners. Or I just use a randomizer. Just random grouping. So you cannot pick up your own teammate. How about that? Why not? Whoever says no is gonna fail. Random is better because random grouping allows you to learn from someone who is completely different, doing completely differently in research. So it really forces you to collaborate with someone you just have no idea. And the project is going to be maybe 2 of you or 3 of you working together on some specific topic in related to optimization. You can all sit down together, find time, and then pick up a topic. Okay. So I will do grouping for you, random grouping. Okay. So I will tell you the results of grouping maybe this week. So you will have almost a month to make friends with your teammate. Okay, I will even randomly select the team leader. So the team leaders are responsible for finding the teammates. If a team doesn't work well, the team leader will be punished. Okay. So after the proposal, I think we will be talking about genetic algorithm. Actually, May 1st. Oh, actually, since we do take-home exams, we save a lot of time. We can actually do more. We don't need to skip courses. So GA here, multi-objective here, / multi-disciplinary here, and then uncertainty, my favorite subject here. And then I think we do, yes, neural network here. And then final presentation, final project. So we only have 2 more exams. For the second half, no exams. For the second half, those 4 topics: GA, multi-objective, multidisciplinary, uncertainty, neural network. Those 4 are the really hot topics in optimization. It's something you need to know. But I'm not going to ask you to do any exams. So for the second half, you will be working with your teammate. The best to have a nice final project is to work on some problem that is interesting for all the members, and maybe try to find try to write some programming codes to truly solve for it. So at the end, if you truly have something good, I will work with you to write a conference paper. So you can have a publication afterward. But I won't publish with every one of you because not every team will do well enough. Only the good ones. I will ask you, hey, do you guys want to write a paper with me? So you can use this opportunity to try and see if we can publish together. If we publish together, of course you need permission from your advisor. So let's say we have 3 people in the team, and all 3 came from different advisors. I will talk to them personally, ask them if you get permission to publish a paper with me, and I will put your advisor's name in the papers. Okay? If any of your advisor refuse to do it, then we don't do anything. Okay? So we can submit papers to international conferences. There are several conferences that I'm involved in the second half of this year. If we publish together, I will pay for the registration fee. So you don't need to pay. And since your registration is paid, you can go to the conference physically. So we will see, okay? I may not be able to satisfy everyone, but I should be able to satisfy some of you and bring you to a conference somewhere in Taiwan, not outside of Taiwan. It's too expensive. So somewhere in Taiwan probably will cost me like $20,000, maybe something like that. That's fine. But if it's outside of Taiwan, it's 10 times. Then it's not. I don't have enough. Okay, so that's it for today. Anything else you want to comment, ask me? Are you guys scared of projects? Don't worry. If you meet someone who is knowing nothing about optimization, then you can grow with your teammate. Okay? And I'm the kind of person who is always happy to answer optimization questions. So whenever you have questions about optimization, just come to me. I'm very happy to answer it. Okay, that's it for today. See you next time. Bye.